the next talk. If Chung, if you can stop sharing your screen and Bo can take over.
Yes.
Okay, Bo, you're still muted.
Can you hear me?
Yes.
Good. And also see the screen? Great. I assume everyone sees my screen now. Okay, actually today, today's talk is all about the uncertainty estimation in your policy setting. So it's also include my talk. I'm Bo, and I'm from Google Brain, and also this work is joint work with Fear, England, Nikon, Chaba, and Dale. Okay, thanks for Scott and Chang's talk. I don't need to talk about the importance of the uncertainty estimation in your policy setting. So I will give a very brief introduction about the notation I use, and then I directly go to the brief recall about linear programming form of policy value, and then I will go to the major part of today's talk, which is what we propose as CoinDICE, and later its conclusion. Okay, here's the preliminary setting, and basically I think everyone here knows the MDP, and I don't need to go through line by line. I just want to give a notation introduction here. What I used later, I use S as state of states, A as state of actions, and T here stands for the transition probability, R stands for the immediate reward. Gamma is a discount factor, and mu0 I assume is initial state distribution. And the policy actually is a conditional distribution. If I give you a state, it will produce a distribution over the action space. And we define the value of policy by expectation over trajectory return, which is defined as you accumulate the reward along your infinite horizontal return, but with some discounted factors. The expectation here takes over all randomness, including the transition operator, the reward, and also your policy. So I think this is pretty much about what I will use in this talk. And also, I will formally define what is OffPolicy evaluation here. Basically, it's there's no chance you can visit the environment, but only a data set from the historic interaction with other behavior policy. And this data looks like a tuple, which is saying you have S0, A0 from initial distribution, and also A0 is conditional S0 and generated by your policy. And as a reward as prime here is from distribution, where it's played by other policies. So basically, you don't know it. You just get some other agent's historic experience. And A prime here came from the target distribution. And our goal is trying to estimate the policy value, which is defined in my previous slide, without knowing the transition operator and also reward. And we also assume we don't know who collects the data. So basically, that means you cannot access to the policy which collect data for you. So we call this task as behavior agnostic or policy evaluation. Okay, until now, I think that's pretty much the brief introduction of the preliminary. And next, I will also recall what Fear introduced on Monday. And I'm not sure, I think not everyone listened to the talk, so I will give a very, very brief introduction about this linear programming formulation for the policy value. Here, the upper three line is the primal form of the linear programming for policy value, and the bottom three row is the dual formulation of this linear programming. Basically, we can introduce, let's look at the primal form. That is saying, the Q function, you want to push through corner such that it's equals to the Q function is in the feasible set such that the Q is bigger or equal to a future backup and plus your current immediate reward. But because the object function is pushing towards the minimal, so it will push this Q into the corner case. So basically, eventually, the solution of this linear programming will satisfy this constraint only in Q equals to the R plus the next step, I mean future backup. And vice versa, the dual formulation actually is saying, talking about the stationary visitation distribution, saying the stationary visitation will be equal to your backup, your historic experience, but with 1 minus gamma, it came from mu0 and pi. Okay. And I think this is the primal dual formulation for the policy value. And here is, because it's so complicated, you see, the constraints should satisfy to every state and action pair. So basically, we don't have any existing, as far as I know, there's no existing solver can solve this problem. Even I give you the policy, even I give you the model. So one way to formulate it is we use the Lagrangian such that it can rewrite to expectation where the sample came from mu0, pi, and the dd. So this is very standard technique. By you just apply Lagrangian to the either primal dual, you will get it ends up like this Lagrangian. And based on this formulation, actually there's many algorithms proposed recently. We summarize it as a DICE family. From last year to this year, at the beginning, I don't think this formulation is realized. And recently, we unify all this formulation into this Lagrangian formulation, and this paper is published this year in Europe. The reason we call it DICE is because we are estimating the stationary distribution correction. Stands for DSA over your behavior, your data collected. And then with this formulation, after you solve this Lagrangian, you get the point estimator of the target policy. So until now, I think I gave a very brief introduction about what happened in past year about the point estimator of the policy evaluation. And now, beyond what Scott and Chang mentioned today about the importance application of uncertainty, actually, back to the history, there are already many papers talking about the uncertainty in two phases. First one is the optimistic view of the how can you handle the uncertainty. Actually, that is the basic principle in the reinforcement learning, saying when you handle the uncertainty and you can access to the environment, you should do the optimistic action such that it will give you the optimal regret bound in the exploration versus exploitation trade-offs. And in the setting where you don't have access to the environment, you only have access to a bunch of data, which is known as the OffPolicy reinforcement learning or batch reinforcement learning. Actually, many papers talking about we should do the pessimistic in the face of uncertainty, which means we should optimize. We should do the safe optimization, such that we are optimizing the worst performance among a set of plausible models. So in either way, we should take care of the uncertainty in our estimation. So that's motivate us to propose some confidence interval estimation beyond the point estimator. So first idea came to us is like, okay, why don't we use the Bootstrap, which is very old but still powerful method, which is doing like this. You collected, you already have the data set, and then you construct your separate data set, DI, by resample from this data set. And then you run, we run the DICE estimator based on this data set, and we apply one estimator. And after you do the iteration, you will get a population of point estimator. And based on this population estimator, based on this set of point estimator, you can have more statistic estimated from this population, like the variance. And after that, you can do the upper and lower bound confidence interval estimation. But the major problem of this procedure is it's so computationally expensive. Solving one dice meaning you need to solve a min-max problem, and this is creating a lot of that. So the nature question is there any way to reduce the competition? The answer is yes, definitely. Otherwise, I will not talking this kind of work today. So what's that? Actually, let's consider this bootstrap procedure. And the variance basically is saying you want to find in the statistically extreme case from this set of estimation. So that inspires us. We can maybe do a smart reweighting such that the reweighting will help me to locate which subset will give me the worst case and which subset will give me the best case. So that's why we inject the minimal and maximal in front of this set, and the minimal with respect to a reweighting to the data set. And this reweighting is definitely you cannot arbitrarily reweight this data set because it will give the trivial solution, say, it locates the worst case, largest single one, and put all the mass along on this sample. So it should be regularize this W in a relative near neighbor of your empirical data set, and in terms of some F divergence.
Sorry, Bo, just to clarify the notation on the slide, what is curly P superscript n-1?
Oh, actually, that stands for the simplex. So which means the W is the simplex summation to 1 and always bigger than 0. And so W is not far away from 1 over n uniform distribution along your empirical data set. I hope this gives you intuition about how this method is proposed. Roughly speaking, this is a smarter way to do the bootstrap. Okay. And are we clear until now?
Go ahead, keep going.
Good. Now, it seems like the optimization terrified me at the beginning because there's so many min-max min and min-max so on and so forth. But actually, the good thing is we can have closed form for the weights, which means you don't need to optimize it. You just, after you get the solution, you just calculate along this one, it's enough. And we also noticed there is some connection between the COVAR, CVAR, and this reweighting scheme, such that when you choose special F, you will recover the CVAR for the lower bound. Okay. And then let's go to see some theoretical analysis. Because this is very short talk, I don't want to talk about details, but we can actually provide the asymptotic coverage of this bound and also finite sample analysis. The thing I want to mention here is actually, you notice here the rate is very fast. It's no longer the 1 over square root of t. Here's 1 over t, which means that the bound is extremely tight. And so far, we almost finished everything about the CoinDICE itself. And any questions? Good. Let's see how we can utilize this CoinDICE to implement the OFU and PFU. OFU here stands for the optimistic in the face of uncertainty, and the PFU stands for the pessimistic in the face of uncertainty. Let's take the CoinDICE for OFU as an example. So basically, every time you use your data set and run the CoinDICE, it will provide you the upper bound. And then you can use upper bound to do the gradient calculation for your object function. And then you use this gradient to update your policy. And then after that, you have a new policy. So you use this policy to collect the data and so on and so forth. Actually, this is in the same philosophy of UCB. Roughly speaking, it's saying you get upper bound, choose the maximal one, and add your policy and collect data, and use that to do another turn of evaluation and so on and so forth. And same thing happens to pessimism. The only thing changes, you're no longer optimize the upper bound, you are trying to optimize the lower bound, and you don't have the access to the environment, so you cannot collect the data. And if you're sharp enough, you will notice that, okay, here is, when you run the CoinDICE, basically it's introduced weight to the historic experience, and it's strongly related to the popular algorithm used in practical called the experience replay. And actually, we can somehow think about that the existing experience replay is actually doing this in terms of either you want to do the exploration, and then you do the, let's go back to the reweighting scheme. That means you want to look at the larger, the sample with larger error. And when you do the safe deployment, that means you reweight the experience with, and only take sample with lower error. And yes, this is some interesting connections. And finally, it's experience about this method. And we compare to the existing method. Basically, the bootstrapping with different, either the burst style or the student T. And this dot line is the confidence coverage expectation, which is, for example, in in x-axis it's 0.6, and the coverage should be 0.6, and the blue curve is always achieve this expectation. And the second row is the length of the proposed length of the computation interval compared to different method. And the smaller the better. So you can see our method is always beat the other confidence interval estimation in terms of both the coverage and also the width. And here's the conclusion. Recap what we have done so far. We propose a series of estimators for behavior agnostic confidence interval estimation. And I only mentioned one here because the other one is quite similar. And so this one gives most intuitive interpretation as you do a smart bootstrap. And also this estimator can be used for implementing the two famous principles in reinforcement learning. The future work is regret bound for the OFU with CoinDICE, and we will release very soon. And actually, this is always bother us. In DICE family, we don't have very good solver. So we are still working on that. And that's all. Thanks. And any questions?
Thank you so much, Bo. Indeed, we'll open up the floor for questions. Okay, well, I'm gonna ask a question, Bo, to get started. If I understand correctly, the procedure is that you have a bootstrap step.
Yeah.
I don't know, was there anything special about that bootstrap? Any conditions in the bootstrap process itself?
No, actually, I just gave a brief intuition why this method proposed. This is not our method. Bootstrap is always existing there. It's not our method.
I see.
We just think the bootstrap is so expensive, and we want to do a smart way. We want to find a smart way to do the bootstrap, which is goes to this. I just want to find the maximal value in the bootstrap and the minimal value in the bootstrap. And I use these two as my upper computation bound and the lower computation bound.
Right. So let me ask the follow-up question then. So you do find these W vectors, and you were talking about how once you found them, W star U, as you were calling it, you can then compute the upper bound and lower bound.
Yes.
But are there any, suppose I want to use this for exploration, right? Let me see if I can explain this correctly. Is there going to be any concern about, for example, recomputing a W at every step? Could you introduce, break some independence assumptions along the way, if that makes sense?
Actually, then these questions go back to the thing where they're still unsolved, which is how you can optimize this kind of problem. Nowadays, it seems like one way is saying every time I just because we have the closed form reweighting, so every time I update my tall and my new, I will update my weights for each sample. And you don't need to do optimization because we know the closed form.
But there must be an assumption on how the data is collected, right? So if we now collect more data based on this confidence interval, what's going to happen?
You mean based on what? You mean the upper bound?
Or maybe I can ask directly, what are the conditions on your data that allow you to provide that upper bound?
Okay. Actually, our paper would say about some assumption along here, which is saying the data is collected. The data collect procedure is like this: S0 and A0 from the your mu0, and you play your condition on that S0, you get another action. And this dpi actually is a little bit confusing. It's like we have a lot of agent. It's like we have a lot of agent, and they collect the data for you, and they just provide the data for you. That's all. As long as it's tuple, like SAR, S prime, that's all.
Right. So now if you wanted to use this inside an exploration algorithm, that assumption wouldn't hold.
No, actually, that's the problem we are dealing with in various actually. So upper bound is there. The upper bound doesn't matter. It's not related to how the data is collected. We assume it's fixed. And your question is about here, which is saying when we apply the CoinDICE for the OFU, what it looks like. Yes, that's a good question. And I didn't have the intention to mention here because the standard story is quite long. But we can chat offline. It's very tedious. I can say that. And I think there's another question.
Go ahead, Li Hong.
It's not a question, but maybe just a quick comment that early in the day, Scott mentioned that the safety robust RL can be related to uncertainty or other exploration. And what I'm going to say is that Bo's talk is an example of that connection, where some of the techniques from empirical likelihood or this minimax approaches are actually some of the techniques that the robust optimization community has been doing. So this is an example of this connection.
And there's a question from anonymous. And yes, this is indeed some problem. We do observe it. So that's why I say there is a series of estimators, and we have other estimators along this line, but I think this is the most intuitive one. So I want to introduce this one. And indeed, you can also do the optimization, but the trade-off is like you need to pay more attention, and you need to pay more attention on the optimization procedure. And also, the bad thing happens is when the data gets larger and larger, you need to keep ON level variable to be optimized. So this is very painful. So there's definitely some trade-off between the stability and optimization computational cost. So I hope this answers the questions.
Okay, great. So this was the Q&A.
Let me see what's the thing here mentioned. Oh, I think I misunderstand these questions. They are talking about the closed form dual expression. Okay, if I understand correctly, Namku and Ducci talking about you ignore dual formulation and you only apply the gradient with respect to the closed form after you introduce dual formulation, and that will introduce some instability. I think after this explicit with dual and the stochastic gradient, we do observe some instability, but not that heavy. There's some subtle difference between the two closed form things. I hope this answers questions.
All right. Thank you, Bo. Are there any more questions before the coffee break? If not, then thank you to all the speakers from this morning again, and we will now take a coffee break and return at 2 p.m. Eastern Time to start again. Thank you very much. See you in a bit.
Bye.